The CPU is the heart of the computer. Think of it as a more sophisticated form of a calculator. To add two numbers using a calculator, we do two things. First, take the numbers we want to add, and second, input the mathematical operation. The CPU also performs a very similar operation. It takes a series of instructions and binary numbers as input and produces a stream of results as the output. The instructions are a fixed set of rules for processing the input. Think of it as a more advanced form of the addition operation in the calculator. What matters is not that you do some math, but that you can take a stream of numbers and perform a series of operations on these numbers to produce results. Since the computer can encode and store numbers, characters, images, and videos using binary numbers, the numbers can represent actual numbers as well as characters, images, or videos. This ability to store different types of data as numbers, take these numbers as input, and perform different operations makes the computer different from a calculator. Once we understand the computer, not in terms of the math it does, but in terms of the numbers it moves and modifies, we can begin to get a fuller picture of how it operates. The computer is a device that can read, write, update, delete, and move numbers around according to a set of inputs and a fixed set of rules called instructions. However, unlike the calculator, the instruction is a pre-written program stored on the computer. The instruction can be mathematical, like addition and subtraction, or non-mathematical, like reading and writing to the memory. All computers consist of at least 4 fundamental components. Since computers move and modify numbers, there has to be a storage area for these numbers. This storage area is called the memory. To say that a computer modifies numbers implies that there is a device for performing those operations. This device is the arithmetic logic unit. It is the part of the computer that performs arithmetic and logical operations on numbers read from the memory. Once the numbers are modified by the ALU, the numbers are written back into the memory. Some means of transmitting numbers between memory and the ALU are required. This transmission line is called a bus. As the CPU requires both numbers and instructions, we have separate buses to transmit them separately. We also have another type of input, transmitted by a dedicated bus called a control bus. To coordinate all these operations, there has to be a manager. This manager is called the control unit, and it performs its job by using a series of signals called control signals, which are transmitted by the control bus. The control unit coordinates the operation of the CPU, ensuring that instructions are fetched, decoded, and executed in the correct sequence. The ALU, control unit, small memory cells called registers, and another type of memory called L1 cache memory, along with additional components, are stored in a single chip called the CPU. There are two main types of control units: hardwired and microprogrammed. Hardwired control units implement control logic using hardware circuits, offering fast operation but limited flexibility. Microprogrammed control units use micro-instructions stored in control memory to implement control logic, providing greater flexibility and scalability at the cost of slightly slower operation and increased complexity. The terms core and CPU are related, but refer to different concepts in computer architecture. The CPU is the main processor chip in a computer. It is the component responsible for executing instructions and managing the computer's operations. A core is an individual processing unit within the CPU. A core typically consists of the ALU, registers, and control unit. Older processors are single-core processors with only one ALU, a set of registers, and a control unit. This limited the number of tasks the CPU could handle efficiently. With technological advancements, CPUs now have multiple cores. Each core can be thought of as a complete processing unit, containing its own control unit, ALU, and registers. This allows modern CPUs to handle multiple tasks simultaneously, improving overall performance. Since numbers must be fetched from the storage area before it can be processed by the ALU, we want that storage area to be as close to the ALU as possible. Storing these numbers in the main memory is not feasible because the access time is not fast enough. We want a storage area that can be accessed almost instantaneously. This storage area is called the register. A register in the CPU is a small, fast storage location that holds data and instructions temporarily during processing. Registers are integral to the CPU's operation, providing the fastest possible access to data required for computation. However, due to the CPU's limited size, the register needs to be small. Registers are essential for high-speed operations within the CPU, while main memory provides a more extensive storage area for running programs and managing larger datasets. The first x86 processors had only 8 registers. To add two numbers, the CPU would carry out the following steps. First, load the two numbers from the main memory into registers A and B. Second, add the contents of registers A and B. And finally, store the result in register C. This three-step procedure looks very simple, but it is the core of how a computer works. All the other steps are preparation to get to this point or housekeeping work after it. Modern computers also have another type of memory called cache memory. The cache memory sits between the main memory and the CPU. It temporarily stores copies of frequently accessed data and instructions from the main memory to improve overall processing speed and efficiency. Cache memory is faster than the main memory, but slower than the registers. It is larger than the registers, but much smaller than the main memory. Modern computers with multiple cores have multiple levels of cache. The L1 cache is the smallest and fastest, typically located inside the CPU. The L2 cache is slightly larger than the L1 cache, but slower. The L3 cache is the largest and slowest. Older processors have the L2 and L3 cache memory outside the CPU, but modern processors typically house all three types of cache memory inside the CPU. We said that a computer takes instructions and binary numbers to produce results. Let us take a closer look at what an instruction is. Instructions, generally speaking, are commands that tell the whole computer what actions to perform. We can classify the instructions into four broad categories. Memory instructions move data between different parts of the computer system. This includes load, store, input, and output instructions. Arithmetic and logic instructions perform calculations and logical operations on data stored in registers. Control flow instructions control the flow of execution within a program by altering the sequence in which instructions are processed. This includes branch, jump, and loop instructions. System control instructions interact with the overall system and manage various functionalities. This includes interrupt handling, privilege management, and processor state management instructions. Instruction formats in computer architecture refer to the syntax of the instructions. An instruction can have three components: the opcode, the operand, and the addressing mode. Instruction format refers to the order in which these components are laid out in an instruction. To add two numbers stored in registers, say R1 and R2, and store the result in a third register, R3, we use the following instruction format, which is equivalent to R3 equals R1 plus R2. Here, add is called the opcode. It indicates what type of operation the CPU is to perform. R3 is the destination register, and R1 and R2 are the first and second source registers. This instruction has three operands, two source operands, and one destination operand. Hence, it is called a three-address format. Let's look at another instruction format. This instruction tells the CPU to move the content of R2 into R1. As we can see, this instruction has two operands, a source operand R2 and a destination operand R1. Hence, it is called a two-address format. There are other instruction formats, such as the one-address format and the zero-address instruction format. Returning to our example of adding two numbers, the two numbers can be specified in many ways. We can use the numbers directly within the instruction, or the numbers can be stored and fetched from the registers or the main memory. The location where the numbers are stored in memory is called the address. To add the two numbers, we need to load them into the CPU's registers. To do that, we need to know their addresses. In computer architecture, an addressing mode refers to how the location of an operand is specified in the instruction. Different types of addressing modes depend on how the address is specified in the instruction. Addressing modes are crucial for efficient memory access and data manipulation within a program. The chosen mode determines how the CPU calculates the effective memory address where the operand resides. In the beginning, we said that binary numbers could represent characters, images, and videos. Now let us look at how binary numbers are transformed into characters on the monitor. A computer takes a binary number and displays characters on a screen through a process that involves several steps. First, each character, whether it's a letter, number, or symbol, is assigned a unique binary code. For example, the ASCII encoding system represents the letter A by this binary number. The second step involves generating a displayable representation. When a character needs to be displayed, the computer references the binary code and uses it to look up the corresponding character in its character set. The computer has a font set that includes graphical representations of characters. For A, the font set includes a specific pattern of pixels or vectors that forms the letter A. Think of the graphical representation of characters as a grid of pixels. While a full font rendering engine would be quite complex, for simplicity, the letter A can be represented as a grid of pixels as shown here. Then, this pixel or vector data is converted to a binary format for further processing. In the next step, the binary representation of the character is sent to the video memory, also called the VRAM. The video memory is not part of the computer's main memory. Instead, it's located directly on the graphics card itself. Video memory acts as a high-speed workspace for the graphics card, storing and providing quick access to the critical data needed to generate the images and videos you see on your screen. Note that in the process we just described, the CPU performs the character lookup in the font set. This is true for older computers, but modern computers generally rely on the GPU to perform this step. Next, the graphics card translates the binary data into visual information using various algorithms from the field of computer graphics. It determines which pixels need to be lit up on the screen to form the character. Finally, the graphics card sends signals to the monitor, instructing which pixels to illuminate to display the character. Thank you for watching the video. I hope you learned something today. Have a beautiful day, and see you in the next video.